Okay, good morning and welcome. This talk is about, as the title says, the computer science behind a modern distributed data store. Obviously, that is a vast topic, and I cannot even hope to cover anything much of the whole topic. So therefore, I have just chosen a few topics, and these are these. So that's resilience and consensus, sorting, log-structured merge trees, hybrid logical clocks, and distributed asset transactions. And I have to admit, the last one I don't even fully cover. So if you don't know what these are, never mind. It's not a problem, because all I can do, if I succeed, is to tell you about each of these topics, essentially what is the problem and how is it solved in an overview manner. So that's all I'm trying. And since I have 50 minutes and these are 5 topics, I have 10 minutes each, and so that will be a bit of a rush. So let's directly go into the middle of things. Basically, the bottom line of the code of this talk is you need computer science and modern results to actually come up with a decent implementation of a modern data store. So let's talk about resilience and consensus. Modern data stores are distributed. Why is that? There's essentially 2 reasons for that. One is you want to scale out, you want to be able to use a lot of computers at the same time, and you want them to appear to be a single database. But there's another reason. You want to have resilience. Even if the capacity of one machine would be good enough, you don't want to run the risk that it breaks. So therefore, you want to have a distributed system just to be resilient. So if one node fails, or maybe even 2, service simply continues. Now, as soon as you have different parts on different servers, then these essentially have to agree on things, whatever they are, your data, configuration data, whatever. The time, say. And so, in a kind of semi-definition, I would say consensus is the art to achieve this as well as possible. And I call it an art because there's no end to the problem, essentially. You can't really solve it. You can just approximate it in a sense, as we will see in a second. If things are well, then this is relatively simple. Your computers are networked, they can exchange messages, and so it's relatively easy to make them agree on things. But it is very hard, provided your network has outages, some machine fails, some disk fails and maybe comes back, or a complete machine fails, or even a complete rack fails, and then comes back with, say, different data, or something like that. And these things here, it's not only they can happen, they do happen. In particular, in distributed systems where you have lots of machines, then essentially every night something will happen. And you don't want to wake up in the middle of the night and have to fix it. You want the system to overcome this problem automatically. And we have not yet talked about malicious attacks or enemy interaction or whatever. So this is just plain failures that happen. Now, in that context, it's a lot more difficult. And so therefore, people have spent a lot of time thinking about these. And traditionally, there are essentially 2 protocols to achieve consensus between different machines. One is called Paxos, it's the older one, and one is called Raft. Traditionally, Paxos was being used. It was published in 1998. And to say the least, it is a challenge to understand and then to implement correctly. It's a lot of fun. I do recommend reading the papers about it. They are really nicely written. So one is by Leslie Lamport, who invented that. And it's an ingenious paper, but it's hard to understand. And if you have read it 5 times, you still wonder, did I really understand all the subtleties of it or not? And therefore, the newer Raft, which only appeared in 2013, has actually been designed to be understandable, actually to be more understandable. Therefore, my advice, obviously nobody wants advice, but here it is anyway. If you are interested in consensus, try to understand Paxos first. The papers are very nice, if only hard. Do this for some time, but do not implement Paxos, not even as a toy project. After you have looked into Paxos, then you can enjoy the beauty of Raft. Read the Raft paper, it's a beauty. It's really nice, it's easier to understand, if not completely easy, but it's easier. But then don't implement this either. Use some battle-tested implementation which you trust. I can tell you that this advice is good advice because if I have not listened to it in every single instance. Okay, I didn't try to implement Paxos, and I have suffered from it. So, but the really most important hint I can give is don't try to invent your own consensus algorithm. Unless you have some kind of time place where you can spend 2 years on your own without time passing outside. It can be a lot of fun, but it's hugely difficult, it's very hard to get right, and even then, if you get it right, it's hard to implement correctly. Right. So now I'm trying to do something which is impossible. I try to explain to you what Raft is in one slide. Here it is. Imagine you have an odd number of servers. We come to the question why it's odd in a second. And your target is that they keep a persisted log of events, say. Together, everybody should have the same log. So everything is replicated to every other machine. What they do in Raft, they democratically elect a leader, and that's why you need the odd number. You want to have an absolute majority to elect leaders. So if you have 3, which is a typical installment, then 2 would have to agree on a leader. Or 3. It's only the leader at any given time which may append something to the replicated log. And the append only counts if not only the leader has appended it, but if it has replicated everything to at least a majority, including the leader. And obviously, this majority has to have appended it and confirmed it to the leader that this is now appended. Now, there is very smart logic in the protocol, essentially ensuring that there's a unique leader. That's a tiny lie. What actually happens is that there is a term number, and in every term there is a unique leader, and provided the leader changes, the term number is increased, and then there's a new leader for the new term. There might be a slight moment in time when both believe to be the leader, but the one with the higher term is always valid. And then, of course, we need automatic recovery from failure. In particular, we, of course, need, if the leader fails, then the others, after a short amount of time, notice that. They don't get any heartbeats from it anymore. And they say, okay, we're still 2, let's elect another leader. The other leader takes over and continues service where the previous one left off. And that's about all I can say, because I have 2 minutes more for this topic. And I just want to mention the paper is there. It's proven to work, this protocol. But then to implement it correctly is still quite hard. So we have actually done it for ArangoDB. I can tell you a bit about this later. Because what you are dealing with is a real-time system. The real-time comes in when the followers lose patience with their leader. And then things have to happen in real time, and we have to make sure that regardless of the load and regardless of what data is stored in there, the leader always sends out heartbeats, with hard real-time limits. And then you have to persist everything and not fail and use failover. And so that's why it becomes difficult. How do we put this to use? Essentially, these changes in the persisted log of events are the write transactions of a key value store, which is then sitting on top of that. So you basically can talk to the Raft leader and can ask for write transactions or can read this key value store. And this then makes a resilient key value store, which can be used as a centerpiece of a distributed system to keep configuration data, to organize failover and stuff like that. Now, this is a link, and I will make the slides public, and this is all clickable. and shows you a nice illustration. I just want to fire it up briefly. This is by the author of Raft, not by me. And you see here 5 servers. One of them loses patience and says, I should be the leader. It asks the others, elect me. They come back and say, well, yes, okay, you are the leader. The leader sends, this is now S5 in this example. It sends out regular heartbeats such that the others don't lose patience with him. Here we have the replicated logs. There's nothing in there so far. And I believe I can play with this and tell I can do different things. For example, I can stop it. Now obviously, no, stopping was not the right one. Resume. I want to kill the leader or timeout or whatever. Oh, now it stopped. Never mind. I'm over time with this topic, so therefore I suggest you play with this yourself. That's a great way to see what Raft actually does. And it's a great illustration done by the author of Raft, or one of the authors, Diego Ongaro. And I highly recommend to read the paper, which is also available on that webpage here. And on to the next topic. You see, we jump from topic to topic because it's a vast area and can just cover a few interesting ideas. Now, a data store usually needs some kind of indexing. And for that, in practice, we usually sort things. Now, sorting is a very traditional computer science topic. So you look at the art of computer programming, you find 10 different sort algorithms, and then on modern hardware, they are all rubbish, essentially all, except maybe one. So the published algorithms, what you know, quicksort or whatever, just doesn't work well on modern hardware. And why is that? It is because traditionally we have just compared different algorithms by counting how many comparisons they have to do to sort, say. But comparing is no longer the problem. The problem is data movement. Such a little laptop can easily compute a lot of stuff, but it can't get the data fast enough. And in sorting, you usually want to sort vast amounts of data, and you just cannot get it into the CPU quickly enough. Why is that? When I was a kid and played with my Apple IIe, then there was a 1 megahertz processor in there, a 6502. And since then, comparison to this laptop here, the compute power in one core, obviously at the time it was only one core, has increased by a factor of 20,000, approximately. Now, single memory access has only increased by a factor of 40. And furthermore, these days you have sometimes 32 cores in a CPU. So that's another factor. And this just means that computation has outpaced memory access by a huge factor of over 1,000. So any kind of sorting algorithms which concentrated in the analysis on the comparisons, this analysis is outdated. We have to analyze how fast we can get stuff into the processor to actually compare it. So that's a huge problem. And what I want to do is I want to give you just a glance to an idea how to overcome that, how to make a sorting algorithm which can actually make use of the computing power of 32 cores in a single machine, say. The one algorithm which actually can be salvaged is merge sort. Let me quickly give you an idea. What you do is you have to, if you want to sort a large array, say, you cut it into pieces, you somehow merge the pieces first. That can be distributed in a sense. And then you merge these segments to make one. That is, you have a lot of segments which are already sorted, and you want to merge them into one large sequence. That's a very, very important operation, as we will see later on in this talk, and it's in general very important. Now, if you naively just compare the lowest element of each with each other, may say, or with one of the, you just look for the minimum, then you have an algorithm which always has to go to main memory to fetch stuff. And you are running into the memory wall head on, and you cannot never make 32 cores busy. Therefore, you have to use something like this idea. You use an intermediate data structure called a minimal heap or min heap. Well, that's a balanced binary tree. Balanced means every path is nearly the same size. Obviously, some might be a bit shorter on the right-hand side here. And the single condition in this heap is that whenever you have a node, the element stored at that node is smaller than the two elements below it. That's a local condition which must be fulfilled everywhere. And I can't cover the details, but it's relatively easy to insert something into such a heap and to remove the smallest, which is on the top here, item, and then fix the stuff. All of that has complexity which is proportional to the depth of the tree, which is okay because that's logarithmic in the total number. So what you can do is you put the beginnings of these guys here into the heap. That's a quick operation. They somehow sink down here and are stored in the heap. And once you have convinced yourself that the guy here is actually smaller than all of these here, then you can take it and put it here as the next element of the sorted thing. So why is that good? The idea is that the heap, by clever management, stays small enough to be completely in second level cache or third level cache. And if you think about what happens if you take one element and insert it here, this syncing procedure, which I haven't told you the details of, has to compare the one thing which is new. Well, you have to fetch that from main memory at some stage, but it has to compare it only to stuff in the heap. And since that fits in second level cache, essentially all comparisons, 95% of comparisons, compare two things which are in the cache. And then, of course, you have to write it out, but, well, that's a cost you have to pay anyway. So that means, with this kind of organization, you can organize a sort on a huge array in memory, say, such that all memory accesses for all the 32 cores running at full speed come from their cache, nearly all of them. And that is enough to make a sorting algorithm which has, if you do top, 32 cores running 100% in top. That is what you want to achieve because you get perfect parallelism for your sorting. Now, this is, of course, now a description of stuff in memory with second level caches. But these days we have a whole hierarchy. You have the processor registers, first level cache, second level cache, third level cache, memory, main memory on the same package, main memory on a different package, different processor. Then you have SSD, then you have spinning disk, then you have Amazon S3, then you have Amazon Glacier or whatever. So it's not the only second level cache. This idea can actually be applied across the spectrum. And you always have to manage data locality these days to get things fast. And if we slightly abstract from this idea of sorting here, that is an idea which is pervasive into all of computer science these days. You have to look for data locality on each level of the spectrum. Good. And on to the next. There will be some time to ask questions at the end, and obviously I will hang around the rest of the day to answer questions. The next topic is so-called log-structured merge trees. I'm going to quickly say what the problem is. If you have a data store, and again, let's talk for this time on a single machine with an SSD, say. If you have a box with 64 gigabytes and a 2 terabyte fast SSD, and you run a data store on that, well, you expect that you can store about 2 terabyte of data. You expect that you can store more data than fits in RAM. But at the same time, you expect that you can write to it in a bulk fashion, essentially as fast as you can write to RAM, because you say, well, the data store sorts it out afterwards and stores it to disk. And you also expect that if you only use, in a reading way, a part of your data which does fit in memory, then you expect the data store to cache things such that accesses are essentially as fast as from RAM. That's essentially the same data locality argument yet again. So therefore, data stores need to have a kind of data setup, data structures, which fulfill these properties. And if you look what traditional B-tree-based structures offer, then they usually fail to deliver in at least one of these two. You can tune them to have good buffer cache and everything, but then writing is awkward because you have to go all over the place. And or you can configure them that writing is fast, they buffer whatever in a writer headleg or whatever, but then read accesses are a bit slow. And so the idea of log-structured merge trees is to, well, you can't really solve this problem in a perfect way, probably, but the idea of these log-structured merge trees is that they offer a good compromise between bulk writing speed and hot set fast reads. And now I'll tell you what the idea behind this is. I shamelessly stole this picture from a web page, which is cited down here, but it's a good picture. A log-structured merge tree organizes the data in levels. Level 0 being the most recently inserted data. And essentially you have to imagine that the data flows in up here and over time ends up further down in the levels. Each levels contains files which are sorted within the file. Again, we need sorting. And you can roughly imagine that each layer contains, say, 10 times as much as the previous one. So the basic idea is that you first store new stuff into level 0 in memory buffers, which are then obviously also persisted to disk for persistence. And these are inserted in memory, typically with some kind of tree structure there. And once such a file is somehow sealed, and there is enough of them, and these here can cover arbitrary regions of the key space, say, then a compaction process in the background comes along and takes a bunch of these and merge sorts them into larger ones, one level below. And here we make it so that everything in here is smaller than everything in here, and so on. And we do this in all further levels, such that if you need to read something, what you do is you start in level 0, trying to find it in one of these guys, and since they are sorted and in memory, you can quickly do binary search and find something. You can even do range scans. And once you do not find it upstairs, you just go one level down, go to the right sorted file, and read from there. If you find it, fine. If you don't find it, go further below. So that's the algorithm for reading. Just go from level to level. And the algorithm for writing is essentially just write on the top level. Now, why does this give you a good compromise for bulk writes and hot set reads? Well, I haven't told you the whole story. So here's the rest of the story. Together with such a sorted file on disk, which is immutable because we only write completely new files whenever we do some compaction, together with such a sorted thing, you store a so-called Bloom filter. It's another very interesting topic in computer science. A Bloom filter is essentially a small memory structure, or small data structure, which allows you to ask, is this particular key in this sorted list or not? And the Bloom filter uses only very little memory at the cost of it can lie to you. But it can lie to you in a very friendly way, because if the Bloom filter says the key is not in this set, then it's always right. It's a proof that this key is not in the set. If the Bloom filter tells you, and it does so in, say, there's a configurable amount of cases, it says maybe in 2% of all questions, it says, yeah, it might be in there. Then you can't be sure. It is allowed to lie about the key being in there, and then in actual fact it's not in there. So why is that useful? First of all, it's much smaller. So the usual buffer caching business of data stores will ensure that the little Bloom filter associated with this larger file probably can be cached in memory. So therefore, when it comes to look for some key, you go to level 0, that's in memory anyway. You go one level below, you see, if it's there, then it's in this sorted range. So you look up the Bloom filter, the Bloom filter says no. Then you know the key is not in here, and you can directly go further down. If the Bloom filter says yes, well, first of all, it might be in here, then you have to look. And obviously, if you go out of the hot set, you have to go to storage and you have to pay the price. But you can be very quick. In many cases, for example, if the key is not in the database at all, you can go right through all the Bloom filters and say, no, we don't have it. And that's quick. So therefore, the Bloom filter business, together with caching on each layer in memory, achieves that you get good read performance for your hot set, which is cached in memory. The level structure and the fact that you just write to the top level in memory and then the write-ahead log, of course, ensures that you have good bulk write performance. And as I said, both can even be optimized with other techniques, but this technique gives you a good compromise. Let me just mention one more thing. If you analyze this carefully, and you can't because I didn't give you the details, but if you look at the details, and there's a lot of more information in this web page, if you look at the details, you notice that all I/O is sequential, at least for the writing. And even modern SSDs, although you would expect that they are random access fast, due to their block structure and their possibilities for erasing and so on, they are much faster if you can write sequentially. So therefore, this technique also makes much better use of modern hardware than other techniques which have to do random accesses all the time. So this works for SSDs and it works equally for spinning Rust. So let's wrap this up by just give you an overview. I said writes go to mem tables in the level 0. All files are sorted, and once they are closed, they are immutable. It's only the compaction which happens in the background, which takes a bunch of these, merges them to something further down. You can use merge sort, so that's fine. And all writes use sequential I/O. And you need some kind of Bloom filters or the more modern Cuckoo filters for fast read. And therefore, you get a good compromise between write throughput and read performance. So because these are nice, they're used all over the place. We use them in ArangoDB, but also Bigtable, Cassandra, HBase, InfluxDB, LevelDB. LevelDB was maybe the first one implementing that. And RocksDB is a fork of that done by Facebook. But also nowadays, WiredTiger, SQLite 4, and MongoDB, because they use the WiredTiger engine. They all use this technology, and so it's fundamental for modern data stores. Coming to the next topic, which is hybrid logical clock. Now, the two previous topics were essentially about a single node in a distributed system. This is now really distributed, as was the consensus in the beginning. The trouble is, if you have a distributed system, then the clocks in your different nodes, well, they are not in sync. There's no way to achieve that. Well, okay, Google uses atomic clocks and GPS clocks and everything. That gets it down to a very small clock skew, maybe 20 milliseconds or even better with atomic clocks. But it's a fact of life. In a distributed system, clocks are off each other. So there's a clock skew. So why is that? Well, there is general relativity. So there's fundamental reasons in physics why you can't get them, but this doesn't play a big role in practice. But in practice, it just happens. Clocks are not perfect. They run slightly faster, slower. With very large amounts of money, you can buy good clocks, and then it's a bit better. But even if you run the network time protocol, you will have some kind of clock skew. You can usually, in practice, between modern machines on a network, limit it to 20 milliseconds. But you see, for a modern data store, 20 milliseconds are actually quite long. Yeah? And so therefore, we have to live with that. This essentially means that if you have timestamps in your system which come from different machines, you must not compare them. Because the clock might be off. Well, if the difference is large and you run something like NTP, well, you can say, okay, certainly this guy happened after this one. But if it's close, you don't know. And that's kind of bad, because quite often you would like to compare different events happening in different places of your distributed system and tell which happened after which other one. So where's this used? Sometimes you want to do conflict resolution. There's two different writes in two different places to the same item. One way to approach this is to say the later one wins. Well, if you can't tell what the later one is, it's a bit of a problem. Now, obviously, if you have logs coming from different places, they have timestamps. You usually want to sort them in time order. Or you want to understand, if you debug something, you want to understand what happened after what. Is it an effect or a cause? Yeah? Anyway, you want to detect network delays, you want to implement time to live in a data store, or whatever. There's a lot of reasons why you would be interested in comparing time, and the fact that you can't is a bit of a trouble. So that's the problem. So what is the idea behind so-called hybrid logical clocks? Hybrid means that it's a hybrid between a normal clock and the so-called logical clock. A logical clock is another idea which I'm not going to cover because it's somehow included here. A logical clock is essentially just an arbitrary number which grows and which you say, well, this is called my clock. It has nothing to do with real time, but it's just considered to be a clock. Now, what you do is that you put a local clock in each computer. This is no problem. This is there, a real-time clock. And you use network time protocol to synchronize them. So you can say, well, the delay, but the difference between the clocks is not too huge. You might even be able to bound it by a fixed value. Now, what you actually want is, and that's the crucial thing, is that if different events on different machines are linked by causality, I'm coming to that in a second, if they are somehow linked by that, then you want that the cause has a smaller timestamp than the effect it causes. That's essentially what you want. And you see, if you analyze this more closely, causality between different nodes can only happen if there is some kind of message. So what you do in a theoretical way, you equate causality with a message is being sent. And then you do the following, which is actually quite a simple and neat idea. This hybrid logical clock, which can be queried on each node has a local hybrid logical clock, uses the fact that every message going around in your system has a timestamp which was taken on the starting side and which was sent along with a message to the receiving side. And the receiving side retains the largest clock value it has ever seen in any message. And if you query the hybrid logical clock on a node, it simply does the following. It considers the local clock, that is the hardware clock, and it considers the largest timestamp it has ever seen in any message, including its own, and it just gives you the maximum. So it simply lies to you. It just takes the largest value ever seen, and well, if it has given out that value already, it adds 1 in some little field and makes it even larger. So basically the secret is lying. So why is this good and why is it not bad? It's good because it achieves exactly this condition with causality. If there's a message going from A to B, and some timestamp is taken before the message is being sent, then the timestamp sent along with the message is larger. It is retained on the node B. And if then you ask the hybrid logical clock for a timestamp after the message was received, then surely this must be larger than the one sent in the message, which is in turn larger than the one taken over there. So if a message has been passed from A to B, then a timestamp taken before it was sent is always smaller than after it was received. Ingenious. It's a very nice little trick. But there's another advantage. Obviously, lying is not very good, but fortunately, time flows. So time passes, and therefore, eventually, assume there's no more messages, eventually, the actual time catches up with the lie. And if there's no more messages, then later on, it can pick up this maximum here, and the local clock is again what counts. So essentially, these lies, they repair themselves automatically. And that's the whole idea. So, it's not perfect, but it ensures that causality is preserved. And it ensures that real time can catch up with the logical time after some time. Yeah, so that's a good compromise. So notice that it's not perfect for all the purposes I mentioned, because if there's no message being sent between two nodes, then you can't expect that the timestamps can be compared. Yeah, so it's not usable for all these tasks. For example, it's not so good if you want to compare timestamps of log entries, because there is usually no interaction. But usually you want to stare at these logs to analyze some problem. And usually the problem is around messages being exchanged. So therefore, it's already then a huge advantage to know that once a message has passed, the timestamps actually compare favorably. Again, there's a link which has a very nice description with a lot more detail, and which is actually detailed enough such that you can type it in and implement it in 100 lines of code. So contrary to Raft, this is actually easy to get right once you have a mechanism to fetch the clock and send timestamps along with the time. And on to the next. So this is the biggest one. It somehow tries to bracket everything together, which we talked about, and a lot more. And there's no chance whatsoever that I can even explain the details of such a thing like ACID distributed transactions in one talk even. But let's have a go at it, just to tell you what the problem is and how a path to a solution could look like. What do you want? From an old relational single server data store, you know ACID. Let me quickly say what I mean by this. You have write transactions which cover lots of data points. You want that changes within one transaction either happen as a whole or not happen at all. That's your atomicity. A transaction is atomic. You want them to be isolated. So if another transaction looks at the data store, what you want is that it either sees the situation before the writing transaction so that it sees no changes applied, or if the second transaction, the read transaction, starts after the commit of the first, you want that it sees all the changes. And that is your isolation. A transaction can never see half another transaction. It can only see the whole transaction or not, according to certain rules. You obviously want that your data is durable. You don't want to tell the client, yes, it was written, and then later when you ask, give it back to me, you want to say, I don't have it actually. And therefore, putting all this together, you want to have consistency within your data store. And you want this in particular in the presence of a distributed system where you have replication going on. So obviously in a distributed system, for this to be fault tolerant, you need some kind of replication. And so you want to have consistency between your replicas. So that's one meaning of the word. But also you want consistency of different data points in your data store, which comes from this atomicity. For example, if I send money to somebody, you want the consistency that it either is still in my account or in the other's account. So the two account numbers should be consistent with each other in comparison to the transactions I do. So that's the meaning of consistency, which is usually meant with ACID. Now, with a relational data store on a single node, you have all these, and there is in the SQL standard, there's descriptions as to what isolation levels there are and so on. And it makes actually programming against such a data store quite easy, because you can relatively easily reason about what changes you do and how things look like at what stage. Now, if you do all your transactions one after another, then this is still relatively easily doable. Well, you just finish the first one, you make it so that everything appears at the same time and becomes committed. But when you want that transactions happen at the same time, and in a distributed system, you of course want to hit it with a lot of transactions which, as best possible, happen at the same time, because you want to scale your write capabilities. In that case, it's a lot more difficult. So why is that? The problem is, once you distribute your data across nodes, then a transaction will touch multiple nodes, because you change in one transaction multiple data points. So you have to interact with a lot of nodes, and they have to change data. Now, during this transaction, and even after the commit, it is still possible that somebody wants to see the state of things before that transaction. It might be an old transaction which is still ongoing. So you have to maintain the consistent snapshot during the changing of all the places in all different nodes. Therefore, you have to hide the ongoing activities all over the place from the eyes of other transactions which are looking. And you have to handle durability in the presence of lost nodes, lost disks, and the like. So therefore, in this whole transaction business, in a distributed system, you have to take into account replication of data, you have to take into account resilience and failover, and you have to think how your transactional behavior and the guarantees you want to give can be upheld in the presence of these problems. That is again what makes it troublesome. Like in consensus, and that is essentially a piece of consensus here, the trouble is not if things go well, the trouble is if things go wrong. Now, in a sense, you can see how difficult this problem is if you look on the market of databases and see which players give you distributed transactions and which don't. And the list of modern, scalable, distributed data stores which do not have distributed ACID transactions is very, very long. And it is really a quite elusive club of a few which promise you to have distributed ACID transactions in whatever sense of isolation level. You can notice that I have put ArangoDB twice here, because in the current implementation we don't have distributed transactions. So in ArangoDB we store JSON documents, and so changing a single JSON document is an atomic operation, and that is also in the cluster. But if you touch multiple documents, we cannot make ACID guarantees as of now. But I have put us here as well, because we have a plan to get there. And hopefully sometime we can see the headline on Hacker News, ArangoDB now with distributed transactions, and then I will be a happy man, provided it works. Anyway, it is hard. Only very few, like maybe Spanner was one of the first by Google, and nowadays CockroachDB, do these promises, and they go to great lengths to actually implement that. So, as I said, I cannot really tell you how this works, but let me just give you the basic ideas behind that. And that will also be my last slide here. I said already, you have to do these places all over the place, these changes all over the place, and they must not be visible so far. Therefore, imagine a store like ArangoDB where you have to exchange the revision of the document. you essentially are forced to keep the old one for those transactions which don't see yet the change, and you have to keep the new one. And if you have multiple transactions going on, you might have to keep multiple versions. So what you have to do in every place where you keep your data, you have to do something like multi-version concurrency control. So you have to keep multiple revisions of the data points. And when a read comes, you have to decide in a rather complicated way which one to actually hand out for that transaction. So that's the first thing. That's not too bad. Now, obviously you have replication, and everything happens decentrally distributed. But the fundamental problem is that you now have to organize it such that you do all these changes, they are not yet visible, but then there comes a time when you actually want to commit this transaction. So you have to be able to, in one moment, switch it over and say, now this transaction is committed. And the results should be visible for every transaction which start after that. If I say after, you always, of course, think about hybrid logical clocks and the trouble associated with that. So that comes into the picture here. So what you need is you need a single place in the system, which then, of course, has to be replicated as well, which says, well, yes, this transaction is committed or not. Now, these switches, they have to be persisted as well. They have to be scalable, so you can't just put them on a single machine, because that would not be scalable. They have to be replicated, because you can't have a single point of failure. You have to implement resilience for them, and so on and so on. And yet, it has to be a single place. Now, one answer is that you somehow run multiple rafts all over the place for these switches and use the Raft protocol to have consensus about the replicas of that switch. And then when the Raft thing has committed, then it's counted as committed. But Raft is slow, it's secure, but it's slow, and scalability is a problem. So therefore, you probably want to be doing something more complicated, which I can't explain here. In any case, you have to implement then the transaction logic, the question as to which version you hand out for a given transaction, all over the place, taking into account these switches. The good news is that these switches can only go from don't know to committed, or don't know to aborted for that transaction. So therefore, they can be very well cached. And that is essentially the secret on how things are done in Spanner and CockroachDB, and we are planning to do something rather similar. In any case, my time is up. We have 2 minutes left. I'm happy to answer questions now. I'm happy to answer questions later. I thank you for your patience. And for anybody who would like to have a sticker or T-shirt or OrangoDB, I have put some here as well. Anyway, are there questions? Thanks. Yes. I repeat the question. Don't you run into problem with the cap theorem? No, the cap theorem is not a problem because it's just true. And you have to live with it. So what you have to decide if you do a distributed data store, you have to decide if a network split happens, and it's going to happen because it always happens at some stage. In that case, you just have to decide what you want to do. Do you want to be available? Then you keep writing on both sides of the split, but you have to sort out the mess at some stage. Either you say customer sorts it out, or you use timestamps and do some conflict resolution, or you use only updates which are good. Or, as in the case of Amazon, you just live with mistakes. If stock levels of books are out, they just send an apology and say, we don't have the book. Sorry, we got it wrong. That's the cheapest in this case. Yeah? Or you decide, I want to be consistent. Then you say, on the smaller half of your system, which is on the smaller side of the network split, you just don't service. No problem. You choose consistency over availability, fine. So it's not as such a problem. It's of course a challenge, but it just means you have to decide. For OrangoDB, we decided that we want to honor consistency over availability, And if you lose contact to half of your cluster, then, well, service stops if important data is over there. Let's first have this question here.
I imagine when the leader fails, the other server elects a new leader. How they do that?
The question was in Raft, I take it, when a leader fails, how do the others elect a server? What happens is that once the leader is elected, let's imagine we three are the rafters. I'm the leader. I just send maybe 4 times a second, I send, I'm still alive, I'm still alive, I'm still alive, I'm still alive, and you receive these and confirm. Now, when I fail, I drop dead on the floor. You two will observe that there's no more I'm still alive. So you have a patience. So that is a random timeout you two chosen. And that's about, say, in our case, between 1 and 5 seconds, say. And once you don't receive heartbeats during that time, you just say, oh, there's something is wrong with our leader. You increase the term number and say, elect me, I'm the new leader, and send out messages to both of us, elect me. And one other server is enough to then answer, okay, you are the new leader, term is up, and you two continue without me. When I come back, I see, okay, I used to be the leader, but now there's a new leader with a higher term. I follow you, that's it. Time is up. Thank you very much. I'm happy to answer more questions, and I'm happy to hand out T-shirts over here. Thanks.